Hello, everyone. I'm glad to see you here. I'm very excited and also a little bit nervous. Today, I'm going to explain you, or show you actually auto reloading for Kotlin Native. But let me introduce myself first. I'm Gabriele. I'm a software engineer at JetBrains. I love system programming language, video games, and messing around with some code stuff. And also, I discovered to be like an average enjoyer of Keynote special effects, which is very important for the sake of this presentation. So let me tell you a story. Everything started like around last year when we announced the stabilization of Kotlin Multiplatform for iOS. We saw some people were very happy about it, and they were asking like, yeah, we need hot reload somehow. While some other people were saying like, it's just not possible, relies on dynamic JVM class manipulations, and yada, yada, yada. But there was a part of this sentence that actually bothered me a lot. This is just not possible. And this is something I don't really like to read sometimes, because in computer science, a lot of things are possible. And it grew me, so you need to kind of actually resize it to not say that it's just not possible, but it just takes time. Because a lot of things in computer science, that just takes time. Because just takes this, for example. We have like a nice, is the video starting actually? Oh yes, now it's starting. We have like a nice iOS app, some code over there. We just change it, and something is going to happen like around, like, I guess, 1, 2, 3. Woo! So this is all reloading Kotlin Native, so it is possible. Thank you. But of course, it's just like, there is more into it. So let's try to take a look at to understand what's going on. First, auto-reloading programming languages can be categorized in two parts. We have languages with managed runtimes, like, for example, Java, C#, or Dart, where there is like a virtual machine giving some assistance regarding class reloading and some metadata information. But for some bare metal language, like C, C++, Swift, and Kotlin Native, this is not possible because they're like less dynamic, I would say. And of course, they need external support from the operating system. Speaking of which, auto-reloading this language is possible. It just works differently. So let's see an example. This is like a simple C game. It's not very hard to comprehend. The code is not important. What I'm trying to understand here, usually to convey here, is that you have like a program, you compile it as a binary, you execute it, and you have your game running. There are like two main important parts here. The first one is the game's logic, or the program state. And it's just by basically updating the position, the direction, and this kind of stuff. And then the second part is the actual game engine's logic, right? Where it gives you support to run the actual user code. So what we do here is very simple. We just cut the code into half. Nice animation. And we have like this guest code and the host code. The guest code is basically just the game state wrapped like in a different logic file. And we compile this as a shared library. Then, in our host, thanks to the operating system support, we just like load this shared library during runtime, and we can run the code by using the dynamic linker APIs to just query the function entry points. So you have your running code, you just execute the game, then you switch, and boom, you have your auto-load, your game. And this is nice because basically it works to the dynamic linker APIs by closing and opening some handle. Unfortunately, there is a bad news because Windows and Linux are quite good with that. They're like, oh yeah, whatever, just let me close this handle, I don't really care. Guess which operating system is not happy with that? macOS and iOS failed miserably because, not miserably, but because like, since some binaries contains Objective-C and Swift runtime code, the dynamic linker is a bit strict about what can you actually do or like unload and load at runtime. So the question is natural, are we doomed? Well, the answer is no, otherwise I wouldn't be here. So let's see what are the possible options that we had. The first one would be introducing a Kotlin Virtual Machine, and that's the option that makes most of the sense, like, for example, like as Dart. While it's a good idea, probably there is also other better ways to do it while reusing existing components. So what about native code patching? Great, actually, that's also a good idea. For example, SwiftUI does that with a framework called injection-free. It works okay-ish through function interposing, but unfortunately, it's a bit, I could say, wonky in terms of like stability, since it relies on some reverse engineering libraries. Therefore, what else? Maybe introducing a customer user space linker. And I see some faces, and some of you may think right now I'm very crazy of saying something like that. It's not very trivial. Am I in the right position? OK. It's not very easy to do. But here's the good news, actually. It exists already from LLVM. It's called JIT linker. And Kotlin native already uses LLVM, so we can do function update points at runtime. But addressing the elephant in the room, which is not great, the question is, wait, iOS does not support just-in-time compilation. Yes, but no, it does. It does. It really does. As long as there is like LLDB attached to the running app, everything is fine. For example, this is my iPhone, and it's trying to run like a simple C just-in-time compiled app. And yeah, that's it. Like, it's working over there. The app didn't crash. But if you try to run your just-in-time application on iOS without a debugger, iOS will just immediately kill without any hesitation. So can we do something about it? Yes, something could be done. Unfortunately, we don't have time to cover this topic because maybe you can browse online. There are like some video game emulators that are able to do that. But then again, so this is what happens. You run an application, boom, that's it, done. OK, so this works for us since like Autoreload actually runs on debug builds. So we are allowed to afford a debugger. So this is totally fine for us. We can work with that. OK, having said that, now let's move to the implementation for Kotlin native, the hottest part. So we wanted to make some minimal changes in the compiler and reusing existing components, but there were two big errors that needs to be tackled. The first one is the compiler's backend, of course, and the second one is the Kotlin native runtime. And speaking about the compiler, we need to make a disclaimer. As some of you may know, Kotlin native uses like a closed-word compilation scheme. That means like given some Kotlin files, you compile them with the Kotlin native compiler, and it produces only like a final binary. And this binary contains everything: the Kotlin native runtime, some standard libraries, every possible code inside there, so we can perform aggressive optimizations on it. However, this does not allow you to give some extensibility outside of this word, right? So what we did was introducing something called split compilation in two modes. The first one is the host mode, which basically produce, OK, the host mode, which produce like a host executable, which contains the Kotlin native runtime, and a bootstrap object, which contains the Kotlin user code. And the second option is the guest one, which produces just like the Kotlin user code without any extra runtime support. Similar to the analogy we made with the game before at the start of the presentation. So now, when this object file is produced, the Kotlin native runtime kicks in and starts like loading this object file through an incoming reload request. And we perform two important operations here. The first one, updating function stubs, so we can change the implementation of functions at runtime. And the second one, which is called state transferring functions, to preserve the objects in memory and allowing them to live in the next iteration. Let's take a look for the first one of the performing function stub update on what happens. So basically, we have like our executable running our bootstrap object, which is represented by this function. So it's just like a main running some hello. And then we have like another version of the code, which updates the hello. So instead of saying ciao, it says hola. Nothing very fancy or interesting. But then what happens? Basically, the user compiles the new code, and Gradle says, hey, the user has changed the code. And then the runtime performs some object loading. And then what's important here, before moving any forward, it stops the word. This is very important, because like all the threads are suspended, otherwise it will be chaos. So moving forward, what's happening underneath is very simple. Basically, we have this nice Kotlin function in assembly. It's not important what's written there. It's just like the idea what's behind, which is linking to this say hello function. And what our JIT runtime does, or Autoreload runtime does, is breaking this link and introducing like renaming the function implementation and introducing another function with the same original name, which is just a stub to it. The idea is quite simple, because basically when you want to update the function implementation, you don't update the original function, but you just update the stub. So basically, at the end of the day, what happens is just literally changing the arrows, and that's pretty it. You have like a new implementation of the functions, and that fixed like an issue. So this was for function stub updates in a nutshell. It's a little bit more complicated than this. I tried to make it shorter. But then what happens to objects in memory? Of course, we need to preserve them, and you also need to keep in mind the class layout, of course. So otherwise, you will get like, I don't know, an integer in a string. That would be weird, right? So assuming we have like a class foo with these 3 fields, and we want to introduce a fourth one, which is the Boolean value, what happens is very simple. We start allocating the new version of foo and copying the new values. So x, y, msg, which is a reference. What about bool? B? Yeah, exactly. We assign a default value, since we don't know which value can be assigned there. But that means also that, for example, for non-nullable types, we can assign null, and therefore we can break Kotlin semantics. And this is nice, because like your program will crash somehow, right? But it's because auto-reloading is very hard to do if you have to keep the programs invariant during the runtime. And regarding the references, it's quite interesting, because like assuming we have like our object graph, and this is like the green one is the new object allocated in memory, and the purple one is the old one. We have like references pointing to each other. So what we do is just basically working the heap and try to update the references to the old object to the new object. So we just move the arrows. And then what's even funny is like we don't need to deallocate the object, because basically since this purple object has no more references, the garbage collector will say, oh, well, this is useless. Let me destroy it. And it will be gone forever. So this brings us to the conclusions, actually. So what's next? Some of you already asked me at the booth, like, can we try this already? The answer, unfortunately, is not yet. We're working on that. But there are like a lot of bugs to fix, of course, because playing with auto-reload is never stable enough, I would say. From both our side and, of course, from LLVM side, that needs to be fixed. And some of the bug evos are gone, so debugging like auto-reloading code is not that funny, I would say, if you don't like reading assembly code. And yeah, we also need to, of course, stabilize this runtime module and do it like a test, and more test. So yeah, and what's next will be the integration with composite reload that Sebastian Selmayr brought last year. So this could be possible. That's pretty much it. So thank you for listening to me, and I hope you enjoyed the talk. And please don't forget to leave a vote, I guess, or something like that. So thank you. If there are any questions, please, I mean, in 2 minutes, 30 seconds, I can try to do something. But otherwise, you can come to the booth later and explain you more. Huh? Version 112?
Well, now it's 111, right? The version of the compose.
Oh, the version of compose?
It's going to be in the version.
Oh, no, I don't know. It's still not yet. It's an experimental feature, so there's no plan yet. Yeah, please? On Android? Good question. I'm not the right guy to ask to it.
Yeah,
But
I already asked it what's going to compose talk, and the JetBrains guy told me to come to you.
oh, did I? With Android, actually, we have some ideas, but I don't know, to be honest. I'm more interested, like not interested, but like more related to the iOS part. But something could definitely be done, actually. So, yes. Yes?
You showed at some points you were compiling with Kotlin native, and in this mode that was splitting.
Yes.
Is that like a custom thing you have, or is it like?
No, it's something that we created also on purpose on this. Because maybe I did not mention, but the auto-reload can work only if you, one of the prerequisites is like, do you have like an open world compilation scheme? Because otherwise, every time you compile a new artifact, you have like the whole program compiled and you should roll it at runtime. That would be weird at the end of the day. So we'll just bring some bloat inside the process space, basically.
And is that something that's accessible? Like, can I compile?
Not yet. Not yet. It's just like a work in progress. We're trying to merge it, hopefully, into the Kotlin repository anytime soon.
Nice.
Yes?
Do you think this will be usable, the split compilation and reload path will be reusable also for non-composed iOS apps, but on Linux and...
Yes, on theory, yes. On theory, yes, but on the moment of practice, we're focusing more on macOS and iOS because of the iOS story. But
putting all the bases in place, so I guess...
yeah, the cool thing about LLVM Jitlink, it has also support Linux and Windows. So on theory, this is possible. On practice, I didn't test it yet, so. No worries. 15 seconds for more questions. Okay, nice. I assume no more questions. So thank you everyone for being here.